HK, HP, what was the symbol that we used for data symbols? A, right? So A
Yes, sir.
n minus L minus B, A conjugate n minus M minus K. Oh, sorry, this should be K cross conjugation. This should be P, right? Plus, and an expectation over here, plus, since the noise is uncorrelated with the signal, this will be simply, I'll skip the noise terms, right?
So
Make
that is
sense?
n minus L minus K or n minus 1 minus K?
Okay, n minus L minus K.
Okay,
This is
sir.
L. See, this is L, this is 1.
Okay.
Fine. So this beast, now this, thankfully, okay, let me clear this. So this thing, thankfully, expectation and not delta L minus M. Fine. Noise is white. Here, the expectation goes inside. So we have already assumed that no, the channel coefficients, right? We have assumed that we know the channel coefficients.
Yes, sir.
Therefore, these are deterministic quantities, and this expectation goes inside, and so let me call this 1. So this first term, therefore 1 equals, this first term I can write as summation P goes from 0 to L, K goes from 0 to L, HK, HP conjugate, expectation, right? Now, assuming the symbols to be uncorrelated, fair assumption? Assuming the
Sir,
symbols to be, yeah,
sir, this is required, like uncorrelation is required out here.
decorrelation or uncorrelatedness, yeah. So what about, so see, you are sending multiple data symbols.
Yes.
So if, so simply considering the simple case of modulation without memory, you can say that if it is modulation without memory, each symbol is independent of all the other symbols.
Yes, sir.
Since each symbol is independent of all the other symbols, in case of modulation without memory, what happens? Okay.
Okay, sir. Got it.
Got it. So this. So yeah, now so this, therefore a n minus l minus k a conjugate minus n minus p equals 0 or equals 1 if L plus K right.
Yes, sir.
Fine. So or n minus L minus K. So I can reduce this to this summation goes from P L plus K, right? Agreed?
Yes, sir.
Great. So this summation, so 1, I can write summation over, or summation K goes from 0 to L, and HK H L plus K minus M fine. So in a way, therefore for diagonal entries, this is case of diagonal entries M equal to L. Therefore this is true. Therefore this what have we used? Believe we have used the term, we have used the sigma. Yes, expectation of sigma LL, the Lth diagonal entry of the matrix sigma. Therefore sigma LL equals, therefore sigma LL equals, what does sigma LL equal? Sigma LL equals summation K goes from 0 to capital L, each K square plus and not. Right? Oh, just a second. This is scrolling. This is scrolling to the right position. Just give it a second. Yeah, plus sigma LL, this beast. This is, yeah. So this is the LS diagonal entry of the matrix sigma. Fine.
Sir, what
And
was sigma?
this sigma I defined. So we last lecture
Okay,
in
sir.
the
Yes,
end we
got it.
solved the we have solved the equalization problem, but we had gotten everything in terms of a matrix and a vector. We are looking for the entries of that matrix and that vector, right?
So this sigma is sigma R, right?
So yes, the covariance matrix of that received signal or received symbol, received signal actually. Fine. And sigma Lk equals K goes or Lm. K goes from 1 to capital L, HL, H conjugate L plus K minus this. Fine. So I can write this as, so this matrix sigma can be written as one matrix this cursive H plus N naught I right. Right. Right.
Yes, sir.
So this is, I don't know why this is laggy today.
So the
But
entries of the cursive H matrix is equal to the these sigma LL and sigma LMs.
so sigma L minus this N naught. So this N naught won't be there because this N naught will only be present in diagonal terms.
Okay, sir. Okay, okay.
Fine. And the other matrix, which is, what is it? We called the vector xi. Did we calculate it? No. Xi r, xi ra. So if I try to calculate xi ra, this equals, what is xi ra? So xi ra is this Rn A conjugate. So now R summation K goes from 0 to capital L HK A K minus K minus L and minus K minus L plus W, right? So xi Ra, the Lth entry is simply fine. This beast. Agreed?
Yes, yes, sir.
Yes.
Yes,
So
sir.
now what we have done is we therefore have a technique of equalizing the seed symbols when the or that results in a minimum mean squared error. Fine.
Yes, sir.
So now have two equalization techniques at our disposal. One, zero forcing equalization, and two, there is something called adaptive equalization as well, and तेरा कौन है? Okay, so nothing. Yeah, so there's some problem at my end. देख क्या? हाँ, thank you. Yeah. So MMSC equalization and adaptive equalization. Fine. So the point is that if you Google equalization, in ISI channels, if you Google this, you will find hundreds of thousands, not hundreds of thousands, but thousands of research papers, if not tens of thousands. So this has been a pretty active, this was a pretty active area in the early or late 80s and early 90s. But overall, equalization is inconvenient. So you might see that so the first thing we notice is that equalization in both the forms that we have discussed requires inverting a large right? You agree
Yes,
with
sir.
this? So it involves inverting a large dimensional matrix, which is at least L times L for length L channel. So which is at least L times L for a length L channel. So what's the problem with inverting a length L matrix or L times L matrix?
Sir, too much competition.
How much?
It
Order of
depends
LQ.
on the algorithm. Yeah.
Big O of L cube. You know big O, small O, right?
Yes, sir.
Great. So equalization, while good, or while equalization was a big idea in 2D and 3D systems, soon lost its charm due to the high loads. So we won't discuss equalization in more detail now. What we will instead do, we will discuss an alternative. But before that, before we start discussing that alternative, it's good to point out that all this discussion done under the assumption that know the channel coefficients. H0 right?
Yes, sir.
All of this discussion is under the assumption that we know the channel coefficient H0 to HL, but the question is how to find these, how do we find these channel coefficients out, right? Guesses?
Pilots.
Pilots. Pilots. So you know the answer.
Yes, sir.
So the answer are pilots. So for the uninitiated, I'll briefly explain how pilots work. So pilots go into the cockpit and fly the plane, isn't it? No, no, not funny. Yeah. So what happens is that say this is the transmitter, this is the receiver, and this is a channel, and this H0, H1 I want to know. So what I will do is at time 0 transmit transmit and pulse with fine. We can do this.
Yes, sir.
So if we do this, then is so A0 equals and known, right? So therefore H0 plus and we do not transmit anything till right.
Yes, sir.
Okay, Adit. So is my microphone as bad as Adit's or slightly better? Oh, cool. Anyway, so what we do now is, so in general, for 1 less than equal to L less than equal to capital L, or 0 actually, 0 less than equal to L less than equal to capital L, RL equals root over EP HL plus WL, where WL is rectified Gaussian noise with variance unknown. Fine? Fine?
Sir,
Yeah, Shubhash.
sir, we start sending the pulse from
We
first
just send
instant.
one pulse. We just send one pulse, one pilot pulse.
Okay.
See, the channel acts as if so when you so there will be residual channel coefficients. That is what we know.
Yes, sir.
That is what ISI is, that at each instant the channel will continue to, even if you don't transmit anything, due to the ISI you will continue to receive something because of the previous symbols that you sent.
Yes, sir.
Fine. So this, and therefore we get this form. What? Therefore, what is this thing doing? Okay. It has decided to embarrass me again. And let me try green. Yeah, green is working. Now RL, oh sorry, equals this. We want to estimate the channel coefficients, or given R1 or R0 to RL, want estimates of right.
Yes, sir.
Yeah, right. So because of this, H0 to HL. So what do we do? Let's look at the general case. Let us look at the, again I will write RL equals root over EP HL plus W. So now let the LMMSC estimate H hat L of HL be CL times RL, right? So what I'm doing is I'm multiplying this RL with some CL that will give me an estimate of HL. Make sense? Because HL is all the information that I
Sir?
have about, yeah.
So why are we using LMMSC? Like, why shouldn't we go for ZFE?
There is there is no zero forcing estimator. 2, we want the best possible estimate of channel coefficients, right? We want the best possible estimate of channel coefficients.
Yes, sir.
So since we want the best possible estimate of channel coefficients, since we want the best possible estimate of channel coefficients, yeah, we want it to be optimal in some sense. Agreed? Want it to be optimal in some sense?
Yes, sir.
Since we want it to be optimal in some sense, we say that we are considering do you hear the Lohardi wala? No.
So something was
Yes.
there.
Yeah. Okay, so that's a waste paper collecting guy for the uninitiated. So we say that we are considering optimization in the mean squared error sense. Fine. So expectation of HN or HL at this should be minimized.
Yes, sir.
So let us say that we restrict ourselves to linear functions of the received data or received symbols. I can do that. Restrict ourselves to linear functions. No complicated tan inverse 1 over x square kind type functions. Restrict ourselves to linear functions. Simplicity. Fine?
Yes, sir.
Yes. So if we restrict ourselves to linear functions, so that kind of an estimate that is linear and is optimal in the minimum mean squared error criterion is called the L. Please, this is not equalization. That's an MMSE equalizer. That's a different thing. We're talking about an estimate. So this is the rationale for choosing LMMSE estimate. Fine.
Yes, sir.
So now, since the only received symbol carrying information about HL is RL, we let L equal, बच्चे बैल हो रही है इनके के लिए, हाँ सॉरी, या H hat L equal CL right?
Sir, then one doubt.
Yeah.
Just few minutes back you wrote that we have two equalization techniques at our disposal. At the first
No,
point
no,
you wrote
we had we had discussed two equalization techniques. After writing that, I spoke for like 3 or 4 minutes. There are multiple
Yes.
equalization techniques. These are not equalization techniques. We are done with equalization techniques now.
Okay, so these
We
are
are estimating.
Okay.
There are umpteen number of equalization techniques out there. I can teach a full semester course in equalization if I want to. That would be wasting everyone's time actually. But I can teach a full semester course in equalization and still not be done with it. There is too much out there. But the point is that what I wanted to convey was there is something called equalization, and for equalization we had assumed one thing, that we knew the channel coefficients. All of that discussion was based on the knowledge of us knowing the channel coefficients, right?
Okay, sir.
So this is how do we get to know those channel coefficients. This is not equalization.
So now we are concentrating only on estimations.
Yes, we are only talking about estimation or
Okay.
channel estimate, say. But the question is, how do we find these out? Know the channel coefficients. Fine. So now, therefore, we have to find the CL so that we get the optimal estimate. So again, expectation of HL minus CL RL whole squared is to be minimized. So this is J equals this is the mean squared value of HL square plus fine. Again, differentiating with respect to, so let me make this. CL conjugate, I get CL, this should be expectation. CL, sorry, the CL expectation RL squared equal or minus expectation HL RL conjugate. Equals 0 or CL equals HL RL divided by this beast. Just a second. Fine.
Yes, sir.
Yeah. So this is actually the MMSC estimate of the Lth symbol or Lth pilot. And this is the MMSC estimate of the, yeah, I'll write it out. This is the MMSC estimate of the Lth channel. Fine. So this is how we obtain the estimates of the channel coefficient. So this is stuck for some reason. Now, so once we have these, so you can actually, since RL equals root over EP HL plus W, letting expectation of HL whole square. What should I call this? Psi L looks fine.
Yes, sir.
So RL equals EP psi L plus N naught and right? Oh, just a second. It's loading. Root over AP psi L. Right? Therefore,
Yes.
CL equals root over EP
Sir,
psi L. Yeah.
so one doubt, when we were differentiating with respect to C star L, then
Yeah.
why is exactly the real part in the, we are no longer bothered with the real part?
We have done this. We have discussed these. We have been discussing this since the beginning of the semester. Go back and look at it.
Okay, got it.
Complex differentiation I have done so many
Yes.
times.
Yes, sir.
Yeah. So, fine. And
Yes, sir.
H hat L equals this. Fine. This is okay?
Yes, sir.
Letting, okay, just a second. This is letting
Yes, sir.
So from the principle of orthogonality, zero, right?
Yes, sir.
And therefore chill. Sorry, chattel H tilde dash. Where and we can decompose the channel into a known coefficient into a known channel coefficient, which is which we know, plus this acts as the estimation error that acts as self interference that has to be treated as loss. So next semester you have this mobile communication course. So there you will come across detailed discussion of these things. So that is an elective that you will have to
So
that you
you're
will have
taking,
to huh?
sir, will you be taking that?
No, principles of communication,
Okay.
because I have already taught that course once. So I have the videos. So I'll be lazy next semester. Not that I'm not that I'm not lazy now. Huh. Not that I'm not lazy now, but I'll be even lazier in the next semester. Huh.
So you don't think
Fine.
we'll have offline classes next semester?
Sorry?
So you don't think that we'll have offline classes next semester as well?
Magical. It depends on some miracle on this, based on the situation right now. Yeah. So anyway, so what I will anyway do now is that so there are two topics left. So I wanted to cover this much estimation. You have done this kind of estimation in the detection and estimation course, right? Something like this.
Yes, sir, like LMMSC we did it,
Yeah.
but not with this kind of application.
These are applications. So these are all, so communication, modern wireless communication is all application of detection and estimation theory.
Yes, sir.
So what, so this completes the discussion on equalization and channel acquisition. So now what we have is OFDM 1, 2, wireless or introduction to wireless communications. These are the two topics left. So I won't be starting any of these today, but let's meet on Thursday and see how much OFDM can we cover. Fine.
Yes, sir.
So tomorrow no class. We'll meet on Thursday and see if needed. So I'll cover OFDM, and if needed, you can refer to that Aditya Jagannatham's course on advanced 3G and 4G wireless communication. And in the first four lectures, he describes the part of wireless communication that we will be covering in this course in quite good detail. So, and his lectures are 40 to 45 minutes, so that is equivalent to 3 of my lectures. So that should be the end of it.